What happens when you mix cigarette smoke, 3D printing, and addressable LEDs with an open source environmental sensor? Yeah, this wasn't my first thought either. Let me introduce you to the Clean Air Necklace, a collection of electronics, 3D printing, clever design, and real-time data visualization, thanks to DesignSpark, who sponsored this video and provided their proprietary air quality sensor module. Pretty cool, huh? The design for the necklace was inspired in equal parts by the irregularity of nature and the bold, flashy looks of power femmes around the world. Apparently it also reminds folks of Ruth Bader Ginsburg, and I'm okay with that. Creating irregular LED matrices is most easily done with LED strips, so I planned my design around that restriction. Because this is a wearable, I wanted to try and keep things small, light, and easy to use. I planned to put the microcontroller for the LEDs at the back of the neck, as well as the power source to keep the visuals nice and tidy. I calculated based on personal measurements that I would be using at least 1 meter of 144 density LEDs, and I wanted to make sure that they were powered consistently and safely. I opted for a small USB power bank and split the power from the source to feed separately into the microcontroller and the LEDs. Throw in a switch to add extra control over the system, and we're sitting pretty. For the LEDs, I chose NeoPixel individually addressable LEDs, but any similar RGB LEDs would work as well. I also procured some simple slide switches and an Adafruit USB-C breakout board to plug the power bank into. For the brain of my necklace, I chose the Tiny Pico V2 by Unexpected Maker because it is ESP32 enabled, allowing it to speak wirelessly to the air sensor module, as well as effortlessly drive the LEDs. I picked this board because it is incredibly versatile, powerful, and very tiny. Perfect for a wearable. You can't make light without power, so getting this circuit sorted had to come first. Hold on to your butts. It's about to get real nerdy in here. I trimmed off the extra pin on the switch and soldered the center pin to the V-bus on the USB breakout board, while the left pin got soldered to the wire that would send the power onward to the rest of the project. The ground on the breakout board was paired up with the power wire from the switch and spliced to send power separately to the microcontroller and LEDs. Hot glue keeps the precious solder joints safe and secure, and we're on our way. Before jumping into building the LED matrix, I wanted to test the LED strips with my setup and see if I couldn't gather a bit of real-world data about the power consumption for 288 NeoPixels. I definitely fell down a rabbit hole around power requirements for LEDs. There's a lot of information out there on the internet. And I've just put some fast LED test code on here. So it's basically the moment of truth. Will it work off the power brick? Let's find out. Let's turn it on. Stuff's happening. Oh my gosh! Oh my gosh, it's beautiful! Look at it. Using the ammeter, I was able to get an idea of the kind of power 288 NeoPixels used at what I would have considered to be pretty dang bright. I'm of course aiming for lower power consumption in the final product, but it also won't be using this many LEDs, so this was a promising test. All right, enough faffing about with rainbows. Let's make a necklace. To ensure that I was making something that I could actually wear, I started with a paper prototype of the necklace. Translating something flat into something curved and three-dimensional is not always as simple and straightforward as it may seem, and paper prototypes are super useful in ensuring a good fit. It also provided the perfect template for sizing up the cut pieces of the strip, as well as laying them out correctly and pre-planning the wiring arrangement. Packing tape is great for sticking the strips down in the correct placement to allow for easier wiring up. And trust me when I say, anything that makes the wiring easier is something you will appreciate when you actually go to do it. Though, let's go back to the wiring arrangement for a second. I chose to feed power and ground lines into all the vertical strips from the top using a homemade bus bar instead of snaking them along from bottom to top. That said, data for LED strips does need to be wired up sequentially because it has a directional flow, meaning I had to run the wire serpentine along the length of the strip to get it to display animations correctly. Is this the only way to correctly wire up such an irregular matrix? Of course not. There are a myriad of methods, and this one just felt right to me. Did I wire it up in the most efficient way? Also no. I realized after the fact that I did not need to run the data line all the way to the leftmost strip and then back to the right. I have no idea why I did that. But hindsight is 20/20, right? 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 Honestly, this part is a lot of wire stripping, soldering, and testing. Over and over and over again. It's totally worth it though. The final step in completing the LED matrix is to correctly set the mapping. For this, I owe a great deal of thanks to Jason Coon of Evil Genius Labs, who not only helped me create the mapping for my unusual setup, but also designed a whole tool to make the mapping of irregular shapes exceptionally easy. Ah yeah, that's the good stuff. Now, nobody likes naked electronics, and when you're putting them on skin, a proper enclosure becomes essential. What better time for a bit of computer-aided design and 3D printing? Yeah, that's what I thought too. You in the back, stop giggling at naked electronics. This is a serious project.
My parts are showing. My goodness. Oh.
I created the design in Fusion 360 to be printed in Recrius Filaflex 82A flexible TPU filament, which meant it could be printed completely flat and bent to fit a human neck after printing. Or at least, that was the idea. Real-world physics worked differently than anticipated. The addition of several well-placed notches along the edges of the enclosure fixed this problem right up, thankfully. I decided to place the power circuit and tiny pico in a drop at the back of the necklace that could be removed if necessary, making it easier to service the electronics and change the code. All of the pieces have their own snug housing within it, and I optimized it to be the smallest possible size while still fitting everything. A little lid fits firmly on top to protect everything inside. Yes, this did mean rebuilding the power circuit to be smaller, but it was totally worth it. For the connections, both between the drop and the necklace itself, I explored some different options, including a variety of magnets. But the winning combination turned out to be dovetail joins, which work surprisingly well in flexible filament. Like, seriously surprisingly well. It can be attached behind the neck without help, and easily pulled apart to detach it. It's also very comfortable to wear. For those of you concerned about safety, the brilliance of a flexible dovetail is that it holds securely with the weight of the necklace, but pulls apart with just a small amount of force if a quick release is needed. I do love a good dovetail. The channels for the vertical strip pieces all print separately to make for easier printing, but required a bit of creativity to attach to the main body of the enclosure. TPU is chemically resistant, meaning that most glues won't work on it. Tpu Welding, which is more or less heating and remelting the filament, creates a strong bond, but requires the right tools to do it. I used a 3D pen and hot metal knife attachment for smoothing. The diffusion for the LEDs is created by placing a bit of fire-retardant polyester wadding in the channels before sealing it up with clear 3D printed panels. The clear Recrius filament is actually too clear on its own, so I created an additional diffusion effect by slicing the files to print with an alternating Hilbert curve on all layers. It also looks very cool. Put it all together and you have quite the statement piece. But it still doesn't really do anything. That's where the DesignSpark Environmental Sensor Development Kit comes in. This piece of open source hardware can be paired with a particulate matter sensor, a CO2 sensor, and a volatile organic compound sensor, all at the same time thanks to the kit's modular design. For my necklace, I'll only be using the PM sensor, but it does look incredibly cool to have all sensors running simultaneously. I added a couple of simple 3D printed belt clips so I could wear the sensor on my hip, allowing it to get air quality readings wherever I am. The ESDK uses an MQTT broker to communicate sensor readings to a server, and that is exactly what I'm going to use to send the sensor data to my necklace. Since this is meant to be mobile, I use a Wi-Fi hotspot on my phone to connect both the sensor and the necklace to the internet. The sensor uses a Raspberry Pi core, which makes connecting to my Wi-Fi a relatively simple bit of code in the system. The tiny pico in the necklace is a slightly more complex process. First, getting it to connect to the Wi-Fi, and then asking it to connect to the specific MQTT client server that the ESDK is using. The ESDK sends a significant JSON payload, but the data itself is rather easy to single out for use in the rest of the script. I created a small bit of code to test the communication between the sensor and the necklace, just to make sure it was responding correctly. I love rainbows as much as the next person, but such an awesome design deserves more interesting animations, wouldn't you say? I mean, I think you would if you could talk back to me right now anyway. I'm using the Fast LED library for creating awesome animations within the Arduino language, which is both incredibly powerful and fast, as the name implies. Now, I'm going to level with you. I'm still very much learning to code and am no way an expert when it comes to this stuff. I am incredibly grateful to all the help and advice I received on using Fast LED and writing code inside Arduino. For this particular project, I wanted to create a base animation that was calm and reminiscent of breathing, with an overlay animation that would be triggered by the sensor data climbing above a certain level. I like the idea of sparks rising up towards the wearer in increasingly vivid and threatening colors as the particulate matter levels rose. The color of the particles is tied directly to the exact sensor reading, with whitish yellow being a mild alert and red being the highest. The actual code uses a huge range of functions tied to the Fast LED library, including custom palettes, patterns, and fading. I've arranged it so that more animation patterns can be easily added to the base as well. If you're curious to dive deeper into my code to see how it's been built, you'll find links to it in the video description. Of course, this is all well and good, but I won't actually know it works until I get some sort of real-world test. It's a known fact that cigarette smoke contains serious amounts of particulate matter, and secondhand smoke is a genuine problem, so I think that would be a great way to test the necklace. But I don't smoke. All right, let's get the sensor a bit closer. Oh, it's going up, it's going up. Yeah, it's working. It's totally working. Oh yeah, it's violet. That means it's really high. Oh, but it's back down again pretty quickly. Look at that. That's fascinating. That's really fascinating, actually. I know what you're thinking. This is great and all, but what does it look like in action? Well, this has been an interesting field test. I did not expect the air in London to be so consistently bad. It's actually been more or less the same particulate matter numbers, whether I'm surrounded by trees in a park or next to cars on the road. And that's a little bit disturbing. It makes for a slightly less interesting pattern, I suppose, but it's very interesting data all the same. So I'm going to consider this test a success. Yeah. A huge thanks to DesignSpark for sponsoring this project and providing the ESDK for me to use. Additional massive thanks to Jason Coon, Hannah of Hannah Makes, and Deborah of Geek Mom Projects, all of whom were incredible sources of knowledge and gave me entirely too much of their time to help me out with this project. If you know your way around a soldering iron and LEDs and want to give making your own fashion air quality statement necklace a go, check out the links in the description to get your hands on the code and 3D printable files for this. If it wasn't obvious from the video, this is not a beginner project, so please proceed with appropriate caution if you do. Make sure you follow me on social media to see work in progress shots of this project, and check out my Patreon if behind the scenes and bonus content are more of your vibe. Top patrons totally get a shout out like this here too. These are all amazing people, by the way. Like and subscribe if you dig this kind of electronics and design project, because I've got some more juicy ideas up my sleeve for future things that might just blow your socks right off. Until next time though, keep creating. I don't know the rest of the song.